All right, BIM 100 students, let's get you ready for Professor Pasquinelli's final. We're going to do a deep dive and really focus on the key must-know concepts from Lecture 3, all about chromatin.
So let's just jump right in with the challenge, shall we? Take a good look at this DNA protection assay. I know, it's straight off a Pastacam and it probably looks a little intense, but trust me, stick with me through this and by the end you are going to know exactly how to dissect this thing and nail the answer.
So here's our game plan. First, we'll tackle why DNA needs to be compacted at all. Then we'll get into the whole open versus closed chromatin thing. After that, we'll walk through the experiment itself. And finally, we'll come right back to this question and solve it together. Simple as that.
Okay, first things first, we gotta start with the most basic question of all. How in the world do you cram all of that DNA into the tiny, tiny nucleus of a single cell?
And I'm not kidding, that's the central problem here. We're talking about over 3 billion base pairs. It's a logistical nightmare. And the cell's solution to this incredible packaging problem, well, that's chromatin. It's why it exists.
And the absolute fundamental unit you have to remember is the nucleosome. Just picture it this way. Your DNA is like a super long piece of thread, and the nucleosome is the spool it wraps around. That spool is made up of 8 little proteins called histones. That's it. That's the first level of organization.
Okay, so DNA is packaged, but here's the really cool part. This packaging isn't just for storage. Nope, it's actually the cell's main way of controlling which genes get used and which ones stay quiet.
You know, a really easy way to think about this is to imagine a library. You've got some books that are locked away in a back room, totally inaccessible. Those are your inactive genes. But then you have other books sitting right out on the table, open and ready for anyone to read. Those are your active genes. And this right here, this is the slide you have got to know. On the left, we have euchromatin. Think U means true or good. It's open for business. The key modification here is histone acetylation. That makes it loose and transcriptionally active. Now on the right, you've got heterochromatin. This stuff is highly condensed thanks to modifications like H3K9 methylation. And because it's so tightly packed, it's transcriptionally inactive.
All right, now for the main event. This is the experiment that Professor Pasquinelli is almost certainly going to ask you about. It's called the DNA protection assay.
And the beautiful thing about this experiment is that it's designed to answer one simple, elegant question. And Professor Pasquinelli puts it perfectly here. Is our gene protected because it's all wound up? Or is it loose and open and therefore vulnerable to getting chewed up by this enzyme called DNase?
So to get the results, you've got to understand the process. It's pretty logical. First, you get the nuclei out of your cells. Then you add the DNase enzyme. Think of it as a little Pac-Man that eats any DNA it can reach. After that, you purify whatever DNA survived the attack. Then you chop up that surviving DNA with very specific molecular scissors. Those are the restriction enzymes. And finally, you run a Southern blot to look for your specific gene of interest and see if it's still there. Okay, time to bring it all home. We're going back to that exam question from the beginning. Let's use everything we've just covered and walk through how to solve it. And we're back to the gel. Now, when you look at one of these, don't get overwhelmed. The entire story, the whole secret, is just to compare the lanes without DNase to the lanes with DNase. You are literally just looking for bands that get faint or completely disappear. So let's actually read this thing. Check out the normal cells. See how even when you add DNase, the plus lane, that band for BCL2 is still bright and strong. That tells you the DNA is protected. It's wrapped up tight in closed chromatin. But now, slide over and look at tumor 1. Whoa. When you add DNase there, the band practically vanishes. So what does that mean? It means in the tumor cell, the BCL2 gene is in an open, active state, and it got totally chewed up by the DNase. Okay, now listen up, because here comes a classic trap. This is a detail that students get wrong all the time, and Professor Pasquinelli loves to test it. Looking at that band on the gel, does its size, where it is on the gel, tell you the size of the entire BCL2 gene? The answer is a big, flashing neon no. And please remember this for the final. The size of the band you see is determined only by where those restriction enzyme scissors made their cuts. It's just one specific fragment of the gene, not the whole thing. It's like looking at one page of a book, not the whole novel. So here it is, your final high-yield cheat sheet for this lecture. Just burn these 4 things into your brain. Acetylation is active. Methylation mutes your genes. A disappearing band means the chromatin is open and active, and the band size comes from restriction enzymes, not the gene size. You know these 4 things, you are golden.
And let's just end with one final thought to connect this all to the real world. Figuring out that a gene like BCL2 is open and overactive in a tumor cell, well, that's more than just an exam answer. That's a huge clue for scientists. So think about it. How could you use that specific knowledge to design a smarter drug, one that targets just the cancer cells? Because that's how this basic science turns into life-saving medicine. All right, that's it. Good luck on the final, everyone.